That's why
Perfect.
you. Okay, I thought you unmuted me. You muted me. Well, so welcome also from my side. I have to bring that window in to the front. Today I talk about power saving mechanisms on x86 processor, and I also talk about power measurement on x86 processors. And since I only have like 30 minutes time, I cannot go that much into depth. If you have questions, then you can ask me afterwards, or you can write down the questions in the chat, and I will try to answer them when Thomas is holding his talk, because there's a lot to talk about. So we start at the core level and then go to the uncore, off-core level, the package level first for the power saving mechanisms. And then later when we're done doing that, we look at how we measure energy on x86 systems, on so what are the interfaces that we could use for an in-band measurement. And if you look at the core level, then the first thing I would like to talk about is that we have some transparent mechanisms for us. So there, when you're running your processor, there are core internal components like white AVX passes or AMX passes that are used for tensor instructions. And when these white passes are used, then typically the power consumption goes up. And that means that for software that doesn't use these components within the core, we could just disable these components and then use a higher frequency. And that is actually what processors are doing. And that will lead to some problems that we can see then in the performance of our programs. And here is a nice picture of that. So let's assume we have two different workloads. For example, your glue work code that holds the communication between the processes and the threads, and then the workload where you actually process your numbers and where you're using the AVX 512 instructions or the tensor instructions. That is here marked red. That is the high workload. And what will happen that during the low phase, when these instructions are not used, the data passes will be disabled. So we internally in the core, the AVX 512 passes will be disabled. Only the lower bits will be enabled. And that means that you get a lower power consumption. Well, that could turn then into a higher frequency with a higher power consumption. What that also means is that you will have a lower frequency as long as you're in that high workload. So what happens when you see then the first AVX frequency is that the core will throttle your out of order the issuing of instructions. So your instruction throughput will go down for a short while. Then it will change the frequency to stay within the power limit. So it will change the frequency band, not necessarily the frequency. And then it will use the full out of order issue window. So it will continue not only running, for example, 2 instructions per cycle, but 3 or 4 instructions per cycle, because now it can be sure that it will not use the power consumption that is too high. And afterwards, after you run your last AVX instruction, after some time, your AVX stuff will be disabled again. That leads to a problem, and that the problem is that you're losing performance here because you're having a lower instruction throughputs due to that out of order throttling, and you're losing instructions here at the start of the low path because you're running in the lower frequency band. And that means that depending on the signal length, if you're altering between low and high, that you're constantly losing performance. So we measured that for Skylake processor, where we see that the out of order throttling was about like 70 microseconds, and here the lower frequency band is valid then afterwards for about 600 microseconds. And these are the times where you are actually losing performance. And the question is now, what can you do against that? And what you can do against that is that you stray like that you just put in some AVX, AVX 512 or TMAL instructions within your low workload, then you will stay at least here in the lower performance band and not have the out of order throttling. So it might be that you can win something there because you don't get the out of order throttling here. You might ask yourself whether you could also lower the frequency to stay always within the limit. Yeah, the throttling will also apply if you already have the lower frequency, because it's applied until the band, frequency band is applied, not the actual frequency. Okay, so a mitigation strategy. I have no mitigation strategy for core frequencies because usually as a user you're not allowed to change these. I just want to include them because often in projects looking at energy efficiency, you lower the frequency and voltage of a core when you're memory bound. And that also comes in with some uncertainty. So yes, you can change the frequency if you're allowed, if you get access to the correct files in your sysfs or to the MSRs that are used there. And the issue is that you will, if you look at that graph, that is for an Intel desktop processor, but the behavior, the blue behavior that we see here is also valid for Intel server processors. So what we see here is the time since the last frequency switch in microsecond. And that means here, if we're looking only at that part here with blue in the upper right, that depending on when you arrive in time, depending on the last frequency switch, you will either have a long time to wait for your frequencies to switch to the new frequency that you want to apply, or you have a low time to wait for that, because internally there's a mechanism which will read the targeted frequency only once after like 250 microseconds or 500 microseconds or something in the way, depending on the processor, and then applying the frequency, which is then the remaining overhead that you see here. That can also depend on the architecture. Here we had a desktop processor with two different architectures. You see here that the other architecture will have a different behavior. It's also depending on the time since the last switch. So there's a lot to think about. And just for you to know is that you should only do that at a certain granularity, time granularity, changing frequencies. Otherwise, you will get an uncertain state on what the actual applied frequency is, and that will not be the thing that you would want. Next thing is core idle states. So when we are not using cores, then we can disable them. There are different stages of disabling cores. It can be from usually running core, then to clock gating and power gating. And the issue is that you cannot actually use that directly, but only indirectly. The instructions that you use for that are only available to the operating system. The next issue is that while you can save a lot of power with that, so you're collapsing all your threads and have only the master thread available in a hybrid parallel program, and then the remaining threads will not use CPU time, the cores can be disabled. The issue is that the cache from these cores that are not disabled is flushed probably, and that can lead to a lower performance. It's also that you have an additional overhead for disabling the cores, which I cannot talk about. But there is good news because, well, if you know what you're doing, you can use user space idle states, which are new to the Intel server processors with Sapphire Rapids. They were available at mobile and desktop processors earlier, but now they are also on Intel server processors. They are also available on AMD server processors. These CPU, these user idle states can be used to bring down the frequency somewhat. So if you're looking here at the left-hand graphic, then you see how much power consumption you have on this processor here. It's in the desktop processor where we check the power consumption here, but the same you would see also on the server processor. We have different graphs for different idle states. On the lower hand then are the idle states of the that can be used by the operating system. These are down here. Then we have the active idle states with a while loop filled with NOP operations, with pause operations, that what we see here, or poll operation that is called by the operating system when you disable C states. But if you can go lower with that, with CO1 and CO2 states, these are the user space idle states that you can use now to, if you know that you're not needing the CPU right now, you're in a busy waiting loop, and you don't want to give back the CPU to the operating system. So you have a very low latency on waking up. That's what we see here on the right side. So waking up the core is like in the hundreds of nanoseconds. But and for that, you get some power saving, I'd say. So one strategy to use that is to use these user space idle states in the Intel MKL, I think, or in the Intel OpenMP runtime. You can also set an environment variable to use that. Okay, here user space idle states directly in your program, and then you won't give your the operating system to interrupt you or schedule something differently or use a C state that you cannot control. Then we have the encore frequency. And the encore frequency is typically handled by the hardware. And yes, there are interfaces by the operating system who give the user access to that. But again, we are HPC users, and most often we don't get the access from the administrator for good reasons. And what we need to remember is that the encore frequency is either dependent on the frequency of the active cores, which can happen for AMD and Intel, but also can depend on the workload executed on the active cores. So if the active cores don't use the encore components, then there's no need in having a high encore frequency. So the Intel server processors might reduce the encore frequency when the encore is not used. Let's have a look at that. Here we had a workload where we changed the workload to something where we now see that where we now actually use the encore. First, we run in the level 1 cache, then in the level 3 cache something, and then we have some time until the control loop sees that the workload changed. That is about 10 milliseconds, which is pretty high, I'd say. So during these 10 milliseconds, you will have the lower encore frequency, which will have then an impact on your program. Then we have another delay until how long? So that is again like for the core frequency, in which time frame do we check that we want to change the frequency. So that is up to 1.5 milliseconds. That is measured on a Skylake processor. That's the time range in which the processor will check whether a new encore frequency should be applied. And then the processor is shortly not available for changing the encore frequency for 15 microseconds, which is not that high. But this here, the control loop, that is a problem here. So as long as you will have to wait for a higher encore frequency on this processor, and we'll see a performance degradation until that, if you're using the encore resources here. What you can do is that you use the second thread on your core, which you're not actively using, and just use it to access something in the encore or in the in main memory, even prefetches, something like that. So you just say, okay, I actually use the encore frequency before in my program I would want to use it. So that is the mitigation strategy. With that, you train the hardware control loop that it sees, okay, the encore is used, I should apply a higher encore frequency, and then you can gain performance. It can have a negative effect on the core frequency, but yeah, you always have to decide which death you want to die. Okay. And then you have other off-core components which are interesting and which will influence the performance of your program. These are like the connection between the processors. These are the DRAM frequencies, the memory controller frequencies. And also they can have some kind of internal mechanisms for changing these and changing these on runtimes. You will certainly see that you need privileged access for control, and that you need either special software or even that you have to access the BIOS. So that's probably not something that you would want to do during runtime of your program, to just toggle these values. You can, if you look up this one, for example, that should be applied to some AMD processors, where you can change the frequency of the I/O die over that. Here we see some numbers for the bandwidth depending on the DRAM frequency, the I/O die P states for accessing memory on an AMD ROM processor. So we see here that obviously the higher the I/O die P state, as lower the I/O die P state, so the higher the frequency, the higher the bandwidth will be. The higher the DRAM frequency is, the higher the the bandwidth will be. So that's something that we would expect. We've also seen earlier that AMD will only get the highest bandwidth if you don't use all of the cores, but only a subset of the cores. So that's also somewhat of expected behavior. If you look here at the DRAM frequency, here we have an I/O die P state versus DRAM frequency, and now we look at the latency, at the memory latency. And here we see that the memory, latency can be lower for a lower DRAM frequency, and that is significant. And then might mean that depending on the programs that you're running on your system, that maybe a lower DRAM frequency would help. So let's say all the programs that you know are basically memory bound, you brought them to the GPU because, well, it has a higher bandwidth, and then maybe only running the latency sensitive, memory latency sensitive workloads on your main processor, and that would then favor probably having a lower DRAM frequency. So that's something to take away for the administrator, to maybe have a look at the programs running on your system, and then maybe you can get some performance optimization from that. I will not talk that long about package idle states, because that will also be an issue that Thomas will talk about later on. It's just that if you use all cores use the C1 idle state, so we talked about idle states earlier, if all cores go into C1 or deeper, then we can see that the frequency of the cores will be reduced. You can disable that with changing one entry in an MSR, and I think there's also an sysfs entry for that. Lowering the frequency of the cores can then lead to that you have to wake up the core and then again change the frequency, which means that you lose some performance in the beginning of the next workload after the idle phase. So you might want to have a look into that, whether you really want to do that, and whether you really want to, whether the saving in power here is worth the loss in performance. If all cores agree to go into C6, then also the off-core components can be disabled. So the uncore and other stuff, the main memory will be put into self-refresh, and that's called package C6. And that's where you get see the significant power savings. That's where you will have the lower idle power consumption that we would expect and that we have seen in server processors, and mostly in mobile and desktop processors. The issue is that as soon as some non-core components are needed and need to be active, and may be only to answer to some cache coherence protocol, the package will be woke up and go to package C2, which is a kind of in-between state. That means the cores are still idling, but the package is not idling that deep. And the problem here is that you only have an indirect usage, so the operating system will decide which to use from that, and that external noise will prevent package C6 states. That can be off-core request on a thread on the other processors that will wake up the processor that could go into package C6. And that's also external devices that can wake up processors. That means that more noise will probably mean less package C states will mean more power consumption, but also less noise can lead to a higher power consumption, because if you don't have that much noise, then it might be that your core decided for a wrong C state, for wrong idle state, and then will stay in that idle state because it's never woken up and never has the chance to revert its decision. Okay. Now to the second part, and that is measuring energy on x86 system. And I want to thank Ondra because he had the talk last time, and he also already introduced the running average power limit. And that's why I can only focus on a small subset of that. So we know that this is provided via registers. It's available on AMD and Intel platform. Here are the domains that are significant on HPC systems. We have the package domain, the DRAM domain on Intel, the core domain only on Intel, but not on Sapphire Rapids, and the per core domain. So that's the power consumption of all the cores, and that's the power consumption of each single core. These are available via sysfs or perf or MSR safe, whatever interface you want to use. And we have some problems. The first problem that we see that it's not necessarily accurate. If you look at these measurements here, that is a Zen 2 Rome processor, we see that ideally you would have for an external reference measurement, we see that here on the x-axis, and on the y-axis we see the measurement from RAPL. In an ideal world, these would fit here on that line, because we have a certain offset for the base power consumption of the system, and then with every watt that you use on the processors on the DRAM, you would have a watt that you see on the external power consumption, and maybe a little bit more because you need something for the cooling, and you have some other overhead. And that's why we would say, okay, it doesn't have to be a one-to-one relation, but it should be on a linear line. What we see here is that really differs, and it depends on the workload that is executed. So we see here that the multiplication workload, multi-PD, that is SIMD parallel multiplication workload, that is using more power consumption, while here the memory copy has a lower power consumption if you compare it against. So you cannot necessarily take the RAPL sum package here as some kind of an given number that you can use to publish your data and say that's the energy that I needed. It's also here in parts because AMD doesn't support the DRAM channel. If you look at Intel and look here at that desktop system, then you see that's also inaccurate. So here we have some kernel with memory accesses, and since desktop systems don't provide the DRAM domain, you see that the projected power consumption is lower. But the problem is here that if you look at the lower power consumption here in that zoomed in part, then you will see that while the actual power consumption of the system goes up from 40 something to 50 something watts, then often RAPL reports only these 1.4 watts on the y-axis. And that means that you also cannot take that seriously. Even if you're using more cores, more threads on the system, the power consumption is still at 1.5 watt and doesn't change at all. So always be aware of that when using RAPL to validate and report energy efficiency of programs. The other problem is that RAPL is too accurate, and that was seen here on that mobile processor by Lip et al. And you already know that you can, depending on the instruction that you're running, you will have a different power consumption, which we see here. We can differentiate between the different functions that are executed and see that in the power profile. So we can say here that was executed, that is an F scale, that is a move operation, that is a cache line flush operation, depending on the power profile for multiple measurements of the same routine using these instructions. What you can also look at here was what they also looked at is that they can, from the power profile, also extract the data that has been processed. So here you see an 8-bit ASCII character, and you see that here that bit 0 was not set. It was that bit 0 was not set, bit 1 was not set, bit 1 was set, and so on and so on. And then you can see that you can extract the data from the power consumption that you have, which is a security issue, obviously. And Intel has a mitigation strategy from that, and this is available on your Intel systems. So here, what we see here is the default RAPL measurement on an Intel desktop system, and we see not the same, but another pattern on Intel server systems, so on Sapphire Rapids. What we see here is that we have a workload and we have different operand weights. So the number of set bits here, no bits set in the XOR operation. Here is half of the bits set and all of the bits set. And then we can distinguish and say, okay, here the same operation, the same instruction were executed. We can see the different data here, here, and here. And that is what you've seen previously also in the server processors. Intel provides something called the filtering mechanism. And this filtering mechanism is always enabled when you're within SGX or when you set the bit 0 in that MSR. What that leads to is that your RAPL reading now looks like that. They just add some random noise. And this random noise will lower the quality of your RAPL readings. So if you still want to use RAPL, even if it's not accurate, and you say, well, on Intel it's accurate, then make sure to at least report whether the filter was active. If you once enable that filter, you must reboot your node to disable and unset that bit. So if you tell your admin, they will probably enable that filter for security reasons. So you might want to do that. Maybe not, if you're interested in accurate power measurements. Okay. The other problem is that you have some unmapped devices. So here's a measurement on an Intel Sapphire Rapids Max system. And here we have a stream. Should say stream somewhere. Change it on the other set of the slide. So this is a stream measurement. And we once put with NUMA control all the data on the HBM memory and the ones on the DDR memory. And yeah, on HBM, we have a higher bandwidth. Who would have expected that? And we also have a different power consumption. So the power consumption goes up to 700-watt package plus 4-watt DRAM for HBM and 640-watt package for 10-watt DRAM. And if you look at the difference between this one and this one, that's more or less accurate. The problem is that I don't trust that number. So that probably doesn't include the high bandwidth memory. And the high bandwidth memory is probably not mapped here and at all. So maybe, is this even measured? Can we, or if that is included in the package, which probably is not, because the higher package power consumption should come from less stalling in the cores because they get the data faster, then maybe we would want only to look at the HBM energy that we use, or only look at the package energy without the HBM, even if it was included here. So yeah, that will not work. But fear not, we have new monitoring features on Sapphire Rapids systems and also on other systems. And this is also available in band. It's probably mostly designed for out-of-band measurement. Look at your HWMON class in the sysfs, then you will see that you have some node power consumption where you can get the power average for each second, and that includes the whole system according to the systems I had access to. These were 3 different kinds of systems. We've seen that the accuracy is reported to be 97.5%, which is, I'd say, good enough. And And then you can read that in that interval. If you don't need the 1 second interval, you can also update that, and then it will be reported, for example, every 5 seconds, and will average over the 5 seconds. If you have some kind of daemon collecting these data, then that might be an idea. The same interface is also used on Grace Hopper to provide some energy or power measurements on the different domains on Grace Hopper. So another thing, have a look at that if you're interested. And the other monitoring feature is the inter-platform monitoring technology, I think. So if you can look at this one here, at this article on the Linux sites, and here there is a device for that also in the sysfs that you can read. Usually it's for out-of-band management services, but you get a definition of what is stored where, and you can also read that in band. What is stored there is you have histograms for each of the cores with 10 bins for frequency usage, voltage usage, temperature, AVX, and TMAL usage. You get the current temperature, the throttling occurrency, the residency in some frequencies and C states, and also other information also for energy related information. For example, the fully integrated voltage regulator for the HBM, where you can get the energy of that in microjoule, which then complements the reading that you can get from RAPL. And that is the short overview on power saving and power measuring mechanisms on x86. And I think I was still in time.